All right, so I'm going to get started if everybody else is ready to go. So this talk is called Building Web-Controlled AR Experiences at the New York Times. And my name is Ramona Harrison. It might not surprise you to find out that I'm a software engineer on the Android team at the New York Times. And for the past several months, I've been working on a project to support displaying augmented reality experiences in our articles in our newsreader application. So that's what this talk is about. I'll start off by saying that before working on this project, I had never built anything with AR before. And in fact, I'm a little embarrassed to say that I had never even done any kind of 3D rendering or graphics or OpenGL work before. So basically, that is to say, I was a total newbie when I started at this 4 months ago. Since I was completely new to this, I had to start at the beginning and really work my way through some fundamental concepts to understand what augmented reality is, how it works, and how the heck to actually build an app that renders some objects on the screen and looks cool to our users. So I'm going to kick this talk off by introducing some of the fundamental concepts behind augmented reality and ARCore. And then after that, I'll dive in to talk about how we built a project around ARCore and ARKit on the iOS side that allowed us to create robust, flexible, and customizable AR experiences for our readers at the New York Times. So some background to start off. Google officially released ARCore 1.0 in February of this year. It had been released as a preview and a beta for some time before that. But February was the first time that developers were able to ship applications to the Play Store that rely on the ARCore framework. So fundamentally, ARCore is both an SDK that developers use to build AR-enabled apps, and it's also a client app that lives on your user's phone and that runs the service that the device needs to provide the AR data to your application. And it gives your app the ability to understand the environment around a user's device and to place objects and information within it. So ARCore is available right now to Pixel 2 devices, along with a handful of Samsungs, including the S7, S8, and S9, assuming they're all running NuGet or later. And also, for those of you who, like me, work on applications that have an iOS version, Apple has released ARKit, which provides a similar feature set. So you should be able to support very similar, if not identical, AR experiences across the two platforms. So let's dive into the fundamental concepts of AR and of ARCore. I'm going to go over 5 concepts that I think together illustrate how ARCore enables experiences that can make virtual content appear to rest on real surfaces or to be attached to real-world locations. So these concepts are motion tracking, environmental understanding, light estimation, user interaction, and finally, anchors. So first of all, motion tracking. So as your phone moves through the world during an AR session, ARCore detects visually distinct features in the captured camera image. These are called feature points. So it uses the change in location of these feature points across camera frames to compute the change in location of the device itself. This process is called concurrent odometry and mapping, and it's one part of the equation that ARCore uses to understand where the device is relative to the world around it. So as you can see in this screen capture, ARCore is detecting feature points in the mortar around these bricks and tracking them as the camera pans across the wall. In the screen recording, I'm rendering each individual feature point as an aqua block. And as you can see, there are quite a lot of them, just in this small area. So during each AR session, you might be tracking many thousands of feature points at any given time in the current point cloud. The motion information that's extracted from these visual frames is combined with inertial measurements from the device's IMU. And this is used to estimate the pose, which is made up of the x, y, z position vector and the orientation quaternion of the camera relative to the world over time. So together, the visual and the IMU motion information are combined to estimate where the camera is positioned and how it is oriented within the real world over time. So as a developer, you can align the pose of the virtual camera that renders your 3D content so that the perspective of the virtual content on your user's screen appears to be viewed from the same perspective that the real device's camera, which is how we're able to overlay virtual content over the image obtained by the device's camera and make it look like the rendered content exists in the user's real world. So here's a test screen recording of some costumes from David Bowie. They're currently on view in the Brooklyn Museum, and the New York Times just released an article to bring these costumes into users' real world space. So these are just scanned with a 3D camera placed in the user's environment, and they can walk around them and inspect them. So as long as the user remains in an AR session, ARCore is constantly improving its understanding of the real world around the device. So it does this, number one, by continuously detecting feature points, like we've already seen. It also looks for clusters of feature points that appear together on the same horizontal surface, like a floor or a table. And when it finds a significant enough cluster of these points, it provides that data to your app as a plane. So ARCore is able to determine each plane's boundary, and it will make that information available to your app. Once ARCore has notified you that a plane has been found, you can use that information to render a plane grid indicating the extent of the plane, and you can anchor virtual objects to its surface. One limitation to look out for in the current version of ARCore is that because we're using those feature points to detect where planes are, if you're looking at a white surface where there's not very many points to detect, you're not going to find a plane. I found this particularly ironic because at the New York Times, we all work at white desks. So I can't tell you how many times I had to walk around the office like a weirdo, pointing my phone at different things, trying to find a surface to test with. So if you embark on an AR project of your own, you'll definitely get a reputation as the weirdo in the office. All right, so light estimation. Light estimation means that ARCore detects information about the lighting in the real world around the device. Unfortunately, I don't have a screen capture to illustrate this one, but you receive the average lighting intensity of a given camera image as a float that you can then use to light the virtual content that you're displaying, so it looks like it appears with the same lighting as the rest of the world around it. All right, so user interaction. As we've seen in the earlier screen captures, users can interact with an AR experience simply by moving around the object. Another common interaction that you'll see, which we also use at the New York Times, is hotspots that become activated when a user moves their camera near to a specified point. Users can also interact by tapping or gesturing on the screen. With ARCore, a hit test allows you to take an XY coordinate that corresponds to a point on the phone's screen that the user may have tapped, and to project a straight ray along the camera's view of the world. ARCore will return any planes or feature points that the ray intersects, along with the pose of the intersection in world space. So remember that the pose is made up of the position and the orientation of a given point. This interaction allows users to select or otherwise interact with objects in the virtual world, including planes, anchors, feature points, those kinds of things. OK, so anchors. You can really think of an anchor as just a point in real world space that you want to track over time. You can define and place an anchor at any given pose. And you might want to do this with a pose that's returned from a hit test. This would allow you to capture the point that a user's tapped at a screen, track it over time, and anchor a virtual object fixed to that location, which is kind of an interesting user interaction. This is important, too, because anchors and poses can change as ARCore improves its understanding of its own position and the environment. So when you want to place an object, you need to define an anchor to make sure that ARCore will track that object's position over time. This way you can ensure that the relationship between your virtual object and the point in the real world from the user's perspective remains anchored even as the device moves around. OK, so now that we've run through those 5 fundamental concepts, I'm going to dive into our experience building a feature around ARCore and around ARKit on the iOS side at the New York Times. This is a mission that we started to explore in late fall of last year, and we finally launched our first Android experience in mid-March. But before I talk about what we built, let's take a look at what our original goals for the project were. OK, so our first goal, maybe it's an obvious one, but we wanted to support AR experiences in our existing application, meaning that whatever we ship, we want it to be part of the APK for our core newsreader application. We don't want our users to have to install a side app or a companion app in order to enable the AR experience. This actually turns out to be a pretty important factor, because it means that we need to rule out any rendering solutions that bloat our APK too much. It also means that we can't craft the experience in Unity or Unreal, so we had to go the Android framework route. Our second goal was that our colleagues on the editorial side needed to be able to publish new experiences outside of our app's regular 2-week release cycle. So we're a news organization, meaning it's super important that the content in our app is timely. So we need to be able to find a way to publish a story with AR content that won't need a new app release once the initial release with AR support is rolled out to our users. We also want to provide as much creative freedom as possible for these experiences and their interactions to be unique across all of the different stories that our editorial team creates. This means we want to avoid any pre-baked flows around object placement and interaction. Lastly, we wanted to be able to author each individual AR experience once and have the same version work across both platforms, iOS and Android. So we explored a ton of options in order to meet these goals. And rather than drag you through each one individually, I'm going to reduce it down to 3 general approaches that we explored. And I'll talk about the essential facets about each one of them, their pros and benefits, and why we ended up going with the approach that we did. So the first approach that we considered is what I'll call the native approach. In this approach, the AR experience, including all rendering and interactions, is handled completely by the native application. So because the rendering is handled by the native side, and there's no overhead of additional components on the web side, the experience is fairly synchronous, and it's fast and performant. If you run through the intro to AR materials that Google provides, one of the first things you'll probably see is the Hello AR sample project. It's a really basic project. You fire it up. It renders some planes. You can walk around and explore. And you can place little Andy figurines wherever you wish in your environment. And it's essentially made up of an activity with a GL surface view for rendering, and it includes a handful of helpful classes for rendering various objects, such as the plane grid, the point cloud, and OBJ-formatted 3D models. Playing with this project was a great way for someone like me to get started with AR. But unfortunately, we realized pretty quickly that a purely native approach wouldn't work for our goals and what we wanted to build. First of all, the AR experience had to be baked in at build time. This meant that it broke our first goal. We wouldn't be able to release new experiences outside of our 2-week release cycle, which isn't ideal when you're a news organization and you want to be sure that your content is timely. We could always customize a bit by passing in a unique remote URL to show a new 3D model asset with each story, but we'd still end up with a set of fairly pre-baked interactions to work with. This could be a great solution for many applications, but unfortunately, it couldn't work for ours. The second approach that we looked at is what I'll call the web rendering approach. In this approach, which is built as an extension to the existing WebVR browser API, the device exposes AR data to the web page via a browser interface. The native app is responsible for rendering the camera image, as well as sharing to the web page all of the important ARCore derived data, like what the current camera pose is on each frame, and data about tracked objects in the real world, like feature points and planes. The web page then takes that information and renders all of the virtual content itself using WebGL or another wrapper library for web rendering like Three.js. The page is completely responsible for aligning the virtual camera with the real world camera and for rendering any of the 3D virtual content which is visible in the user experience. The WebAR on ARCore and WebAR on ARKit projects are an example of this approach. Both of these projects have come out of Google, and they're super, super fun to play around with. I really, really enjoyed some of the samples that they've put out there, and working with the Three.js library is a breeze for rendering. So I'd highly recommend taking the time to look through these libraries and try them out, because they're awesome. So just to break it down again, the web page in this case is handling user input, it's positioning the virtual camera, and it's rendering all of the virtual content, while the native app is responsible for rendering the camera image, exposing the camera pose, and exposing the projection matrix. There are a lot of advantages to this approach that we really loved. First of all, iOS and Android versions of the WebAR on ARCore and WebAR on ARKit projects adhere to exactly the same interface. This means that our creative teams would only need to craft one web page for a given AR experience, and it should behave the same on both platforms. Secondly, since all of the virtual content rendering is handled by the web page using the Three.js library, there's a huge range of creative freedom left open once each app release ships. This means each new experience that we create can be super unique, and it doesn't need to adhere to a standard formula when it comes to how a scene will be rendered or how a user might interact with virtual content. However, in the end, we ultimately steered away from this approach, and that was for a couple of reasons. First of all, because the camera image is rendered by the native application on the GL rendering thread, and the virtual content is rendered by the web page in its own thread, there's a slight mismatch in synchronicity between frames. So this means that when the device moves around, it often appears like there's a slight drift between the virtual content and the real-world camera image. This can be a little disconcerting for users, and it really breaks you out of the experience of feeling like there's a seamless connection between the world that you're seeing around you and the virtual content on your screen. Secondly, the Android implementation of these libraries relies on an experimental Chromium fork that we would have needed to package with our APK to support this approach. This would have broken our first goal, where we wanted to be able to provide AR experiences in our existing app without bloating the APK size too much. So the third and final approach that we looked at is what I'll call the web-controlled with native rendering approach. I think this is a nice combination of the other two approaches, and it's what we actually went with and what we're using in production today. In this approach, all of the rendering related to the AR experience, including rendering the camera image and rendering the virtual content, is handled by the native app. The web page is overlaid on top, and in Android, this is just a web view on top of a GL surface view. The web page might display its own HTML content in its view, but most importantly, it acts as a controller for the AR experience. So this means that the native app itself remains as agnostic as possible to the content of the experience. It doesn't care what virtual models are being rendered, when they are placed, or how they are positioned. The native app just exposes an interface for interacting with ARCore or ARKit and with the renderer. It then lets the web page decide what to actually do during each experience. So some of the benefits of this approach. Because we've moved the rendering of both the camera image and the virtual content to the native app side, we now have completely synchronized the drawing of each frame. This means that we won't have any drift resulting from a discordance between the rendering frames in the web view and the rendering frames in the native application. We've also gained some performance by moving these intensive rendering operations out of the web view. And we've retained a high level of flexibility for the web page to customize the experience, because the native app itself is as agnostic as possible to the content of the experience. The web page has the flexibility to decide which virtual models are being rendered, along with when and how they're placed, how they're positioned, how they're scaled, and how they're rotated. It can also overlay any HTML content that it wishes or other JavaScript components to enhance the experience. So before I can talk more about the interface we designed for this relationship between the web page and the native app, I need to do a quick detour to talk about scene graphs. In case anyone here is like me, I had never heard of or worked with a scene graph until earlier this year. So what is a scene graph? Well, a scene graph is a super common approach to managing data in graphics engines. And it's at its core an N tree, meaning that it's a tree made up of nodes where each node can have as many children as it wants. In our world, each of these nodes in the scene graph has some information associated with it. It has a unique ID. It has a position and a rotation, otherwise called its transform. And it has information about what to render. This might be geometry referencing an OBJ file. It might be textures, which are what we're going to place on top of the model to give it the image that you see on its surface. It might be information about its visibility, whether or not it's transparent, and all sorts of other properties that define its appearance. Altogether, like I mentioned in the previous slide, these nodes form an N tree, where each node might have 0 to n children. They all descend from a single root node, which itself is attached to a scene anchor. And remember that an anchor is an object that ARCore gives us to track a real-world position across time. So with this scene graph, we'll allow the web page to control loading and unloading a scene, selecting a scene anchor, setting a node's transform, setting a node's visual properties, and we'll let the web page perform the other administrative tasks that it needs to start and stop an AR session and to load and unload scenes, as well as listen for important events that come from the ARCore session. So we know now what we want to do, but how do we do it? How do we achieve this communication loop where the web page is able to control the scene graph, the AR session, and get information back about what's going on? So this is where commands and results come in. The idea is that we'll create a command and result loop. Commands are created and issued by the web page, and they're passed to the native app via a JavaScript interface that looks something like this. You can see once the native app has set this interface on the web view, JavaScript can now invoke the OnCue function and pass a JSON formatted command through to the native app to process. The app processes the command and sends a result indicating a success or failure, along with any result values, back to a function on the web page via the web view's evaluate JavaScript function. So this is how a command is structured as JSON. You can see that we have an ID identifying the command, a type which will define what the command actually does, and any other required data stored in the options map. In this case, the command is for loading a scene, and the required data that we need is a URL where resources for the scene can be located. The native app then processes the command and sends back a result to indicate that it was successful. In this case, there's no return values from the action, but if they were, they would go in the values map. This creates an interface for the web page and the native app to pass information back and forth that's relevant to the AR experience. So what kinds of things can we perform via this command loop? Well, just to name a few, we can get the AR configuration and find out information about whether or not the device supports AR. We can request camera permission, which is something that's required for an AR experience to start out. We can initialize AR. We can get a plain hit test, meaning the user can touch an XY location on the screen that the web view intercepts. It can then decide to send that through as a plain test to the native app and get back any information about planes that that hit test might have intersected. We can also set the scene anchor. We can load a scene. We can set the node visibility, and a ton of more interactions with nodes. In fact, any that we wish, because we can continue to add to this interface and version it as we go. So altogether, the loop looks something like this. The web interface OnCues a command onto the native app interface. It then goes through a processor that parses the command from a JSON string into a Java or Kotlin type that we can work with. That gets consumed down by a presenter, which passes it to the view, acting on it, rendering it with whichever rendering technique we might choose, whether this is on the iOS side or the Android side. It then invokes a success callback, which will pass any information that we need back to the web page via onCommand result. So you might wonder, what about things that happen in the AR experience that the web page doesn't trigger? For example, how does the web page find out when new planes are discovered by ARCore or ARKit? Sometimes it needs to pull for certain data that it needs, like the transform of nodes. But what about events that happen spontaneously, like when a new plane is detected? What about when the device is running out of resources like memory? We need some way to notify the web page. And for this, we've created event listeners. So events like, what's going on with the current tracking state? Does the AR session have any idea where the user is in the real world? What kinds of planes have we found? What's the download progress of the assets that we need to render our scene? And how much memory do we have available on the device? For this, we've created the Event Listener Loop. So event listeners give the web page a way to listen for events that happen spontaneously. This saves the web page from constantly polling for certain events. Instead, it can set a plane update listener and be notified by the native app, for example, whenever the ARCore session discovers a new plane. So to add an event listener, we do that through our normal command and result loop. We have a special type of command called add event listener. It takes an option specifying the type of event that it should listen for, in this case, download progress. It returns an ID as the result so that events from this listener can be identified in the future. After the event listener has been added, any time that this specified event happens now, the native app is going to notify the web page via the OnEvent function that we've added to our web interface. This is an example of what an event message looks like. So it indicates the type of event, the listener ID that it was sent from, and any additional data related to the event that the web page might care about. So in this case, the additional data that we're sending is related to download progress. It lets the web page know how many bytes are remaining to download in the scene that we're currently trying to load. This way, the web page is able to show a loading progress indicator while the user waits for the scene to load, so they don't bail on our experience before they even get started. So all together now, we have our native interface with the OnCue function. We have our web interface with the onResult and onEvent functions. We have our scene graph. We have our command and result loop. And we have our event listeners. And by putting these components together, we've been able to deliver awesome, unique stories with AR content outside of our app release cycle. And that allows our users to interact with our app in new ways, like bringing David Bowie's lightning bolt suit from where it's being displayed in the Brooklyn Museum in New York here to a park in Turin so that our readers can explore. And I think that's pretty cool. OK, so of course, no fun project is complete without some lessons learned. So we went live with Android support for AR articles in March. What did we learn? First of all, web views are super expensive. So this isn't such an issue when the web view is the only thing that lives in a given activity or view. But when it's rendered alongside a GL surface view, it quickly becomes apparent how many resources are being consumed. So if you do go the route of combined web and AR, make sure to pay attention to how often the web page is being repainted, and do whatever you can to reduce that. And look out for other resources that it's consuming. That's going to go a long way in keeping your frame rate nice and smooth for users. Second, memory, memory, memory. Being an Android developer in 2018, memory limitations luckily are not something most of us need to think about and struggle with on a daily basis. But depending on how complex the geometry of your 3D models are and how high res the corresponding textures are, they can consume quite a bit of memory. So this, combined with the overhead of the ARCore session, means that it's super easy to hit an out-of-memory situation, especially on some of the slightly older devices like the S7. So do whatever you can to reduce memory overhead. If you're displaying lots of models with textures, this might mean dropping to a lower resolution. And we also implemented a low-memory event listener so that the native app can notify the web page if it does hit a low-memory situation. This means that the web page can choose to downgrade the experience, possibly by providing endpoints for lower resolution 3D models. And lastly, use method tracing to track down those bottlenecks that prevent you from hitting your desired frame rate. So the new method tracing tools in Android Studio 3.1 are awesome. I've been using them a lot lately, and they're great. And every millisecond that you can track down and save really does a lot when it comes to hitting that smooth frame rate and making sure that the experience is performant for your users. So that's it for me. Thank you so much. We don't have time for a Q&A, but please come and talk to me anytime if you have questions about AR or about our approach. This is something I'd really love to work towards open sourcing in the future, so I'd love to hear about your own plans for AR and if it's something that you might use. And of course, I can't finish this talk off without mentioning that the awesome Android team at the New York Times is hiring. And thank you all so much for listening. I hope you have an amazing time over the next 2 days listening to some great talks.